Hello. Today we shall be speaking about applications of the derivative. Now, the applications of derivative are diverse. Plenty of applications, all in all real-life problems and scientific problems. But what we have done in the past is that we have been talking about the existence of derivatives. But now, what about the application themselves? Now, there are applications in many variety of even mathematical disciplines, like, for example, finding roots of functions, for example, the approximation of functions, the expansion of functions in the form of series, and all these sort of applications. And in this lesson, we shall be handling those, trying to summarize most, or at least some, of the most important applications of derivative. Now, the derivatives, for example, you can maximize and minimize functions, for example. You can, of course, find the roots, like, for example, in the intermediate value theorem, where you can nest, for example, through a sequence, the root, etc. But in this lecture, we shall be dealing with some important ones. First of all, the mean value theorem. And then we shall be speaking about Tailor formula, which is one of the most important formulas for expansion of functions. And then we shall be speaking about function approximation. Now, they look only to be three topics only, but actually they are wide and they have wide application. First, for the mean value theorem. Now, the mean value theorem relies upon a lemma called Rolle lemma. And this lemma tells you the following. If you have a function which reaches two equal values at two different points A and B, for example, then there must exist a point in between at which the derivative vanishes. And this is actually, you get it by intuition. Why? Because if f dash of c, for example, in the interval of AB is not equal to 0, so sure f dash of c, f dash, the derivative must be increasing all the time or decreasing all the time. But if it is increasing or decreasing all the time, so there won't be any feasibility that there will be 2 points at which f of A is equal to f of B. And therefore, since f of A is equal to f of B, then this contradicts the assumption, and therefore there must exist a point C at which the derivative vanishes. This is called, as I said, Rolle's lemma. And here it is. This is Rolle's lemma. You have any function, for example, at which f of A is equal to f of B at two different points A and B. So most probably it will rise, and then it will go down again. It will climb here to a maximum point, and then it will decrease again as value. And sure, there must be, since it's continuous, so sure, and differentiable, so there must be a point C at which the derivative vanishes. Now, from this, you can, of course, we can take, for example, a very simple example like this one here. Here, for example, this function here attains two equal values of 8 at the point 1 and 3. So sure, there must exist a point between 1 and 3 at which the derivative vanishes. So what we do is that we differentiate it, we set it out to 0, and you find that C is equal to 2. And in fact, so lies in the interval from 1 to 3. So the theorem is correct. Of course, the lemma is correct, but just we take an example to demonstrate it. Now, from Rolle theorem, you get a very important theorem called the mean value theorem. The mean value theorem, it tells you the following. If f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a point zeta in AB satisfying this expression here. And this actually you can obtain it easily from Rolle's lemma. How? Is that you can, here, for example, you can assume that there is a function f of x is equal to f of x minus f of A minus f of B minus f of A divided by B minus A times x minus A. Now, if you contemplate here f of x, capital F of x, you find that capital F of A is equal to 0. Why? Because if you substitute x by A, this cancels out, and here this cancels out too, so you get f of A equals 0. But also f of B is equal to 0. So from Rolle's lemma, since capital F is differentiable because it's composed of small f, which is differentiable and continuous on AB. So capital F here, it is equal to 0, both at A and B. In other words, it attains the value of 0 at two different values, A and B. So there must exist a point zeta at which f dash is equal to 0. If you differentiate this, you got f dash of zeta here minus f of B minus f of a divided by b minus a. In other words, you get f of b is equal to f of a plus b minus a f dash of zeta, where zeta is a point lying between a and b. And this is exactly what it is written here. And this is called the mean value theorem. Why? Because you can write it otherwise. You can write it in this form here. Here you have a, and here you have b, and here you have f of b, and this is f of a. So this is the difference here, is f of b minus f of a. Of course, if you divide f of b minus f of a divided by b minus a, what you get the tan of this angle. But the tan of this angle has not to do with the derivative of the function. But actually it is, because if you take a line which is parallel to this line here, this line touches the graph at point zeta. So in fact, this angle theta is the same as this angle. So you have here that the quotient of f of b minus f of a divided by b minus a is equal to tan of this angle, or the derivative at some other point here on the graph, because the graph is continuous, the function is continuous and differentiable. So you get here f dash at the point zeta in between. Now this theorem gives you why it's called the mean value theorem, because it is the mean value of the function. Suppose that y represent distance, for example, and you take, for example, an example like Rome and Naples, for example. They are far by away by each by 200 kilometers. So here, for example, this is the distance at for example, you start your journey. For example, you want to go to Naples, from Rome to Naples at 10 o'clock, and for example, you arrive there at 12 o'clock in the morning, for example, at noon. So the difference between the two is 200 kilometers. You divide by 2 hours and you get 100 kilometers per hour. In other words, your mean speed will be 100 kilometers per hour, which is the distance between the two cities divided by the time of the journey. But then the theorem is important because it tells you something different. What it tells you? It tells you that there exists at least one point in between Naples and Rome in which your speed reaches 100 kilometers per hour. So although your speed is 100 kilometers, this is the average speed, but still there must be somewhere during the journey at which you have reached this speed. Of course, there may be 1 point or 2 points at which you reach this speed. And for example, here we have, for example, here it is. For example, you can take, for example, let's say this point here, and you have another point here. And this is the difference in y. Here it is, all this, divided by the difference in x. And if you apply the mean value theorem, what you get here, two values of zeta. You had zeta 1, zeta 2. So what you have here is f of b minus f of a divided by b minus a is equal to derivative at 2 points, not only at 1 point, but at 2 points. In other words, you may find that the theorem tells you that the difference between the value of the function at two different points a and b is equal to the distance between the 2 points times the derivative of the function at some points in between. You may have one, or you may have more than 1 point, zeta 1 and zeta 2, in which they satisfy your theorem. So here again, this is the theorem, and you can of course apply it to, for example, the same example. This is the same example, and you watch out for the interval 1 and 2. You have f of 1, for example, is equal to minus 8, f of 2 is equal to minus 13. You can apply the theorem. In other words, minus 13 is equal to minus 8 plus the difference between the two, which is 1 times f dash of zeta. For example, and you have f dash of zeta minus 5. So is there a point at which the derivative is minus 5? Yes, zeta is 1.5, but 1.5 lies in the interval from 1 to 2, so it's true now, the theorem is satisfied. Now this theorem actually is responsible for most of the applications of functions. Because if you wish to calculate the value of the function at a point, and then you can use the value of the function at another point plus the difference between the two times f dash of zeta. For example, you can use the theorem to prove the following. Sine A minus sine B under the modulus value is equal to modulus A minus B. So what you do, you can apply the theorem. You have f of B, or f of a minus f of b, is equal to a minus b times the derivative of the sine at the point zeta in between. So, but you know that the cosine range from minus 1 to 1. So when you take the modulus, this is less than 1. So you get this inequality here, that the difference between the sine function at two different values a and b is always less than modulus a minus b. And of course, you can apply the same, for example, if you wished, for example, the difference between the tan function between 2 points A and B. This is equal to what? This is equal to the modulus. You apply here A minus B times the derivative of tan, which is sec square of zeta. But the sec is always greater than 1, so this gives you modulus A minus B. So you see how we can apply the theorem in reaching many applications and inequalities between values of functions. Now, Tailor formula. Now, Tailor formula is responsible for approximating a function by a polynomial. You have here your function. This is your theorem. It tells you. Tailor, in fact, was a contemporary to Newton. He was living at the early 18th century. This is if a function f, together with n derivative, is continuous on AB, on the closed interval AB, and differentiable n plus 1 times on AB, it takes the following expansion. So here you have f of x is equal to f of a plus x minus a f dash of a plus etc. and plus a remainder term. If you contemplate this expression here, it tells you directly that the value of f at a certain point x is equal to the sum of many terms. The first one is the value of the function at some primary or point at which you begin the expansion at another point f of a, plus the difference between the 2 points times the derivative of f of a. Here you notice that if you truncate here, you get the mean value theorem, except there that you have to put f of zeta, because of course, if you truncate it, you have to add the remainder term. So always you have the remainder term, because this is not an approximation, this is an exact expression for f of x. If you add up after n terms, the remainder term. So here you have the relation between the value of the function at x and the value of the function with its derivatives, f of a and f dash of a and f double dash, etc., n times at another point a. So you expand the function between a and x, and the remainder term, it will be at some point zeta. So for example, if you truncate here, so you add up the remainder, it will be at zeta, so you get the mean value theorem. If you want to keep this one, then you have to add the remainder here. So you put here zeta and you truncate the theorem. And this theorem, in fact, here is the theorem. This is Tailor expansion. For example, this is a sine function. And you want this sine function, you want to approximate it by a polynomial. This is the idea. So for example, let us say we take the sine function. So, and you choose any point, let us say you choose a point x, and you increase n. When you increase n, you obtain this one here. This is the first approximation, because you have f of x is equal to what? F of a plus x minus a times f dash of a. X minus a is a straight line. And then if you keep increasing n, what you obtain a better approximation to your function. At any point x, and you keep approximating, you keep increasing x, look at that, until they almost overlap, or they always coincide. So the idea is that you have a function and you wish approximated by a polynomial. Because what you have here is a polynomial approximating the function. The more terms you take, the more you represent the function properly. And again here, if you, for example, you have the logarithm of x. Now, suppose you take, for example, this point here. Well, this point here, if you take as many terms for your points, suppose you take this point here, and you go back again. For example, this is your first approximation, and then you increase your number of terms. So when you increase your number of terms, you are in fact approximating the logarithm through a polynomial. So here it is. You do the approximation until they fit together. Sometimes they don't fit. Why? Because it's a problem of convergence. In other words, if you choose, for example, the element in which you do the expansion here, then here you have problems of convergence, and we shall speak about this in the future. In other words, you have to watch out. Even if you increase the number of terms, you never can get them to be coincided, because you have to have an x which is less than twice the value of this point here. This is a problem of convergence, and we shall not investigate it now. So here we saw that you have a function, and you wish to approximate this function by a polynomial. In other words, you represent the function by a polynomial, and there always be a remainder term which goes to 0. Now, of course, you may have, as I said, you may represent the polynomial. As I said, you can take only 2 terms, and it will be the mean value theorem. And you may take 1 term, you may take 3 terms. The more number of terms you take, or the small the distance between the point x at which you want to evaluate f of x and the original point a at which you expand, about which you expand the function, you get a better approximation. So you have a function, you wish to approximate it by a polynomial, there will be always a remainder. If you want the remainder to be small, in other words, you want them to coincide and to approximate the function exactly in the form of polynomial, what you do, either you increase the number of terms of the polynomial, or you lessen the difference between the point at which you do you wish to evaluate your function and the point about which you want to expand your function. So here is your function, for example, and you want a first approximation. So here it is. This is the exact value. This is the exact difference here, this one here. It's called delta y. And this is the first approximation. dy is equal to dx f dash of x. We saw before that we said that f of x is equal to f of a plus x minus a f dash of zeta. This is the mean value theorem. This is exact. There is no approximation here. So if instead of this you put x, so what you have here, f of x minus f of a is equal to dy, and this is equal to dx, so you get f dash of x. And this is, in fact, your first approximation of the Tailor expansion. And this is shown here exactly, because here you have dx, and here you have the slope is equal to f dash of x at this point a, and the difference is equal to dy. But the exact value is not dy, is delta y. So in order to obtain delta y, you have to take more terms, or the whole expansion, or the whole Tailor expansion. So here again, this is, as I said, this is your function, and you wish to approximate it by a polynomial. So this is the polynomial that approximates the function f, and there always you obtain always a residue. And in order that this series converges, in other words, you can sum it all, you have to have this tending to 0. And in most situations, when you expand the function by Tailor, you have to take the limit of this remainder. If the limit of this remainder tends to 0, then you are sure that the Tailor expansion exists, and you can find, as a matter of fact, the condition for convergence of your series. Now, the first n plus 1 terms are called Tailor polynomial, and it's of degree n. And then the rest is called, the rest are n of x, which is the remainder. This exists after n plus 1 terms, but the n plus 1 terms are of order n. So, and this is why we call it the remainder after n plus 1 terms, or the remainder after a polynomial of degree n. And so long that when you take the limit, when n tends to infinity, this one tends to 0, so what you have, in fact, that the limit of f of x becomes equal to the polynomial. In other words, both, they coincide when n tends to infinity. So the idea is what? Is to approximate locally your function by a polynomial. That's the idea behind Tailor expansion. Here, for example, you have the function sine x, and you want to expand it around the point pi by 2. So what you do, you substitute in the Tailor expansion. You have Tailor expansion, it tells you what? It tells you f of x is equal to what? F of pi by 2, which is equal to 1, plus x minus pi by 2 times f dash of pi by 2. F dash of pi by 2, derivative of sine at pi by 2 is 0, times f dash of pi by 2, which is 0, plus x minus pi by 2 square over factorial 2 times the second derivative of pi by 2, which is minus 1, so you get minus 1, plus x minus pi by 2 to the power 3 over factorial 3 times the third derivative, which again is 0, and then you have here the fourth derivative. And of course, there is always a remainder, and this remainder must tend to 0 as n tends to infinity. Here you have an approximation of fourth order of sine x. In other words, you have succeeded in approximating the function f of x, which is sine x, through a fourth order polynomial. Of course, it is not exact. They don't coincide. In other words, sine x is not exactly equal to this one, but is equal to this expression plus a remainder, which if you continue like this, it will attenuate and it will go to 0 by taking more and more terms. Here is your, and actually this is the one that I showed you on the applet. This is your sine x, and you wish to approximate it at the point pi by 2. So you see here, this is the fourth order polynomial. Of course, when you have, for example, a polynomial of fourth degree and you apply Tailor expansion, you find that the remainder is 0 because you already start with the fourth order polynomial and you want to approximate it by a fourth order polynomial till it's series. So you get the same thing. But if you have a function like, for example, this one, the sine x, and the derivative proceeds indefinitely, then you always, if you truncate somewhere, then you have to find a remainder. And this is why here you have a difference. Of course, the difference widens up when you are away from the point. So either you have to take more points or you have to take a point near the point at which you do the expansion. So, and it is better if you increase the number of points. And in fact, this is the way how calculators work. Because you know that calculators, they work by doing numerical calculations through the 5 elementary or the 5 algebraic operations. They are the plus, negative, division, multiplication, extractive roots. But if you have a function which is not an algebraic function, like this one, sine x, what they do is that you can transform this function into an algebraic function, in which sense you can transform it into a fourth order polynomial or a fifth order polynomial as you wish, and you always have a remainder term. So the more, of course, you have a machine, and the machine can do a tremendous number of operations, so you can transform this into a Tailor expansion. There is software doing that, and you can always calculate this function. This is called a Maclaurin expansion. The Maclaurin expansion is exactly like the Tailor expansion. The only difference is the Tailor, you expand the function around a point A, whereas in Maclaurin series, you expand it about the point x equal to 0. The difference between the two is nil, except that probably Maclaurin proved it in a different way by assuming that it's a series, power series, and then he differentiated once and twice, etc., until he got his expression. The Maclaurin series is like the Tailor expansion, and again, you can differentiate it and integrate it if you wish, and you may also have a condition for the convergence of this series. For example, and here the same, you get the idea of approximating a polynomial, a function by a polynomial. You have f of x, this is the function you wish to approximate it by a polynomial, and this is the polynomial, and you always have a remainder here. And this remainder, sometimes it's written in the Landau script here, or notation here. You mean that this is a term that what you mean here is that you approximating the function by a polynomial locally around the point A, and here you have a remainder which tends to 0 when n tends to infinity. This is an example here, for example. This is the exponential function. This is a Maclaurin expansion of e to the x, because e to the x is equal to f, you expand around, for example, the point x equal to 0. So it's equal to f of 0. E to the 0 is equal to 1, plus x, f dash of 0. So e to the x, again, of 0 is equal to 1 times x, plus x squared of a factorial 2 times the second derivative, which is again 1. And you go on like this. And if you want to truncate the series, then you add up the remainder here, and the remainder again tends to 0. Here you see, here when n tends to infinity, you don't have a condition for convergence, because this goes to 0 as n tends to infinity, whatever the values of x, because the more you increase x, the more you can find more terms until this attenuates to 0. These are some Maclaurin series. This is here. This is the binomial expansion for k. Of course, if k is integer, positive integer, then it's finite. But if k, Newton, in fact, he's the one to have investigated this problem. When k is a fraction or negative, it goes up indefinitely. And you have here a condition of convergence for this series. And the condition of convergence, you can do it easily. How? Is that you can find an expansion of this through Maclaurin at the point x equal to 0. So, for example, when x equals 0 is equal to 1, plus plus x times the derivative of this, which is k times 1 plus x to the derivative to the power x minus 1 at x equal to 0 is equal to 1 times k, so you get k, x, etc., and you get the series, and then you write the remainder, and you find the remainder containing modulus x. So you, in order the x to the power n, I mean, so in order that this remainder tend to 0, you must have a modulus x less than 1. So this, you get this formula or this expression or this condition by writing the Tailor, the Maclaurin expansion, and then from the remainder, in order that the remainder tends to 0, you end up with a condition of this sort. Here, for example, the expansion of e to the x, you don't, when you write down the remainder, you find that there is no condition on x, and it's always convergent for all values of x. And this is the logarithm of 1 plus x. Here, the condition of this one is the same of this one, because when you differentiate ln 1 plus x, you got 1 over 1 plus x, and again 1 over 1 plus x is 1 plus x to the minus 1, and it's a polynomial with power minus 1, so they almost have the same condition of conversion, except that you have to check for at the end points, at the point 1 and minus 1. These are Maclaurin, again, expansion for other functions. Obtain Maclaurin series for the function square root of x squared plus 1. Of course, you can use Maclaurin expansion or Tailor. Tailor and Maclaurin, in fact, are the same. They follow the same procedure, and the expansion is the same, except that the point A is another point. For Maclaurin, you take it around the point x equal to 0. So sometimes you don't have to use the expansion because you already have expression for some functions. For example, this is a binomial expansion of power half. And here, this is the binomial expansion. You can go back to the Tailor, or you can deduce it. You say at the value y, you expand it around y equal to 0, so you get 1 plus y times the derivative, which is 1 over 2 twice square root of 1 plus y at 0 give half, plus half times half minus 1 divided by 2, which is 1 over 8y squared, etc. And this is the condition of convergence. Since you know this one, all you have to do is you substitute for y by x squared, and you get your expression of Tailor series. In other words, you don't have all the time to resort to Maclaurin series. You can use the expression in or the lists that has been provided to you. Here again, the logarithm of square root of 1 plus x over 1 minus x. Again, here this is easy. Either you integrate 1 over 1 plus x, but since we will not be using this, you can use the logarithm of 1 plus x. We had it in the table, and you substitute x minus x, so you have this one. You notice the difference. They are the same, except x is equal to minus x, but you have to watch out, and you invert the condition of convergence, the inequalities here, and then you take the square root of this expression here outside the logarithm, which means half the logarithm of 1 plus x divided by 1 minus x. In other words, what you do is that you take half the difference between these two expressions, and you get this new formula here. Now, the Tailor, one of the main applications of Tailor expansion is the approximation of functions. Functions, usually, the algebraic functions, they are easy to be calculated, the value of which can be calculated easily because you can resort to your calculator. But what about sine or the exponential, etc.? Your calculator can only manipulate with algebraic operations. But what about if your function is not algebraic? So what it does is that it has to, there is a program which transforms your transcendental function, for example, into an algebraic, into a form amenable to algebraic operations. How? For example, it can be approximated by a polynomial. In other words, by a series of power functions. And since each of them is an algebraic function, therefore you can perform the operations or the numerical calculations. So the function approximation mainly, in order to calculate functions that are, or to approximate functions that are not algebraic, it transforms them by Tailor expansion into a polynomial easily to be calculated. For example, here, sine x. We know very well that for small values of x, you can approximate, for example, sine x. Approximate is equal to x. You can also, for example, approximate, for example, 1 minus cosine x to be approximately equal to x squared over 2, or for example, e to the x minus 1 to be almost equal to x in the neighborhood of the origin. All these approximation, sine x almost equal to x, etc. It's not exactly equal to x. There is a remainder because we know that sine x using Tailor is equal to x minus x cubed divided by factorial of 3 plus x to the power of 5 factorial of 5, etc. Whenever you do a truncation here, you have to add up the remainder term. There is a remainder term here. So the idea is to calculate the remainder term and see what is the bound for the remainder term. So here, for example, sine x is equal to what? Is equal to x minus x minus sine x is equal to x minus x cubed divided by factorial 3 times the derivative, because here you truncate after two terms. Instead of truncating after the first term, of course you can say this. You can say that sine x is equal to x plus x squared over factorial 2 times the derivative of the sine, which is cosine x at a point in between. But instead of saying this, you can, in fact, what you do is that you can take the third expression for, in other words, you truncate after x squared. This is better. Here, in other words, sine 0 is 0, plus x f dash of 0, which is cosine 0 is 1. So you get the first one term, plus x squared divided by factorial 2 times the derivative of cosine, which is minus sine. So you can say that sine x is equal to x minus x squared of factorial 2 of sine e zeta. But this is better, of course. You truncate after the second term and you get, this is exact, this is not an approximation. But then, since you are approximating sine x by x, then this is the remainder. Is there an upper bound for the remainder? In other words, suppose you say that sine x is equal to x only. Would this be a value acceptable for sine x? It could be yes, if you can check a bound, an upper bound for the error that remains in your calculations. Now the error here would be about what? Will be of the order of x cubed divided by factorial 3. So if, for example, you take x is equal to pi over 18, in other words, 10 degree, for example, and you wish to calculate the sine of 10 degree on your calculator. So 10 degree, you can take sine of 10 degree is equal to what? Is equal to 10 times pi over 180. In radian, and you say this is approximately the value of sine 10 degrees. But the problem is that, is your approximation all right, or would you accept this? Would you find this acceptable? Well, it depends on your error. Here is the error, which is the remainder. Now the error is of the order of x cubed. All you do is that you can substitute x for your angle here, pi over 18, and you find that the error is 9 times 10 to the minus 40. So you say, yes, I can almost approximate sine x by x, and you see here that sine x in the neighborhood of the origin is equal almost to a polynomial of degree 1, which is this line here. For example, suppose you want to find a value for the Euler number e, an approximation of Euler number e. So what you do is that you can calculate the value of the function when x is equal to 1, and that's the value of e. So what you do, you expand e to the power x around the point, for example, 0. And you say, for example, when you approximate around the point x equals 0, you get p naught. These are sequence of functions, p naught, p1, p2, and each one you have a Tailor expansion. You take the first term, second term, or third term, and then there will always be a remainder. But you can forget about the remainder now, and you can say when you have a stabilization in the result, you say this is the value of e to the power x at a particular value of x. Here is Pn of x. This is the expansion of e to the power x at any value x when you truncate it to n plus 1 terms, and you have a polynomial of degree n. So what you do, you have a sequence of functions. You have p naught of x. You take this to the first one, or you take 1 plus x, or you take the second one, and this converges. In other words, they sum up to e to the power x. Now, when you substitute x is equal to 1 to obtain e to the power 1, which is e, you get the first approximation of e is equal to 1. Now, the second one is equal to 2. The third one is 2.5. And you see that it converges to 2.667. Of course, you should take P4, P5, etc. And the more you take terms, the more you get a better approximation. And this is probably one of the ways of calculating the Euler number E. As I told you before, one way of calculating functions that are not algebraic or even algebraic functions. For example, suppose, for example, you want the square root of 32. The square root of 32 is equal to what? You want to obtain a value for this. You do an approximation. So you write the square root of 32 as 32 minus 4, and you get the 6, square root of 6 out. So you end up with this formula here, and then you expand this by this is what? A binomial of degree raised to the half. So it's equal to what? 1 plus half times to the minus 9 plus half times half minus 1. Exactly when you do the binomial when n is integer, etc. And you can keep one or two approximations. You can, for example, say it's almost equal to 6, but 6 squared is 36, it's not 32. So you say, I'm going to take the second one, or I'm going to take the third term. So if you take three terms, you get a better approximation for square root of 32. Or the calculator, for example, it can take 3, 4, 5 terms until there is a stabilization in the result. And this is the way how approximating functions occur. Now, in this lecture, what we did is that we saw some applications of the derivative, because the derivative itself, as it is only means only rate of change, but it is not only rate of change that the application of calculus. Calculus is not meant only to be calculating the rate of change, but it's meant to be applied to a diverse fields of real applications. You find applications in economics, you find application for maximization, and it's called optimization. You find application in physics, application in finding roots of functions. So here we have exemplified some of them. We started by Rolle theorem, and you said Rolle theorem is the theorem or lemma behind the mean value theorem. And the mean value theorem is actually one of the most important theorem in calculus, because the idea behind is to approximate a function by a straight line. In other words, you expand the function f around a point A, and you obtain the value of the function in relation to the value at A at another function at another value at another point f of x. So f of x will be equal to f of A plus x minus a f dash of point zeta, and this is the first approximation. And when you do this, you can apply this to a variety of functions in order to approximate this function. And we have applied this to many of the functions. But you have to watch for something, is that this mean value theorem is only one aspect of a larger theorem called Tailor expansion. So in fact, Tailor expansion, the idea of Tailor expansion is that you have a function. It's not necessarily to be algebraic, it could be a transcendental function. And the idea is to expand this function by a polynomial, or that you expand it locally around the point through a polynomial. In other words, you have a function, sine, cosine, e to the x. Can you transform this function into a polynomial? Yes, you can, but there will always be a remainder. And if you truncate this polynomial by taking smaller number of terms, you can reduce it until you get the mean value theorem. But if you expand it, the more you take terms of the Tailor expansion, the more you get a better approximation of the function. And we have seen application of this in, for example, approximating, for example, square roots, etc. And this is, in fact, how machines work. In order to evaluate values of functions that are not amenable to algebraic manipulations, because they are not algebraic functions, what they do is that they transform this into a polynomial, and polynomial, because they are sum of algebraic functions, therefore you can apply your calculator or your computer and you can sum them up. With this, we, I think, came to the end of our long journey of studying derivatives, and we started by the limit, then the continuity, then the differentiability of functions, and then we end up with application of the derivative. Next time, probably, we shall speak about another concept or other applications of calculus. And until we meet, I'm just reminding you again, as in all the other lectures, that there will always be a place of these lessons on the Uni2 Telematic University platform in which you can always consult whenever you wish. And until we meet again, I wish you good luck and thank you for your attention.